that. Okay, so here we are at limits. And so we're just reviewing a straight line. And remember the equation y equals mx plus b. What does m stand for? Slope. And b stands for y-intercept. Good. And so to find our change of y over change of x, that's going to be used a lot. Our rate of change. Our change of y, how do we get the change of y? y2 minus y1. And how do we get the change of x? x2 minus x1. Yeah. x2 minus x1. And so change of y over change of x is also called the rate of change of y with respect to x. Now, some of this is going to be just a new way to say things. Okay, so we'll have to get used to that. So the delta y over delta x is the rate of change of y, the change of y, with respect to x. It's a new way to say some stuff here. So how quickly is y changing relative to x? So if my slope is 2, then basically my y is changing 2 times faster than my x. Okay? So if delta y is positive, then y is, your change of y is a positive value. And it's increasing, yep. And if change of x, so that's, right? If that change of y is negative, then y is decreasing. So here's an example where my change of y with respect to x, or my delta y over delta x, is positive 5 over 2. So for every 5, we go up. We go to the right 2. Make sense? So how can this be interpreted? I can speak. So an increase of 5. So when x, or let's say when x is increased by 2, then y is increased by 5. So this I'll review right now, right? Some new terminology. Guys, can you stay here? Focus. Clearly, I love that word. It's one of my favorite words. Clearly, then, we can say that the greater the rate of change of y with respect to x, the faster y changes. So a low rate of change versus a high rate of change. Clearly. Can I help you, Sam? Clearly. Okay. Okay, so can you find the equation of the linear function that passes through 2, 1, and -4 and -9 in general form? Can you solve that right now? Because you just got this, because often general form is the more proper form. It's like curtsying. It's proper. I know we all hate it though. It's useless. Remember, the first question we ask ourselves is, do we have our slope? Do we know it? Nay, not yet. We can find it by going y2 minus y1 over x2 minus x1. Right? So your first point you can call x1, y1. Your second point is your x2, y2. So difference of the y's over the difference of the x's. But it has to be the same order. Okay, so go ahead and solve this. No, don't guess. So -9 minus 1 over -4 minus 2 Gives you negative 10 over negative 6. What can you divide both of those by? 2. And then also what cancels out? The negatives. So it becomes 5 over 3. Right? Divided by 2?
Yeah, I know.
Okay. So then we want to go from there. Is we have to ask, do we have our y-intercept? No. We have 2 points. We can choose either one. I like to work with the one with positive values. And we're going to have to use our point slope formula. Good old grade 10. It's been a while since you've seen that. It's amazing. 2 years can fly by. So y minus, it's the same thing as slope. It's just derived from slope formula.
No, I was thinking we use this already. As in already this year.
Yeah, pre-calc. Yeah. So y minus 1 equals my slope, x minus 2. We can do this without a calculator, Tyler. Right? Oh, you got to trust yourself a little bit more. Sometimes you got to make mistakes. It's how we learn. We all do. I do. Remember? That's why I need to make cake. When most of you are gone on a field trip. Just kidding. Sure. Sure. Who's going to bring the pie? Okay. So 5/3 x. What is 5/3 times negative 2? Negative 10 over 3. Yeah. Right? This is like 2 over 1. We multiply our numerators, multiply the denominators. Okay. Now what? Add 1. Sure. So we're really adding 3 over 3. Right? Because it's add a fraction, common denominator. So if you had negative 10 over 3 plus 3 over 3, what does it become? Nope. Because you have a negative 10 plus 3. No. Okay, let's get rid of our fraction before we bring the y over. What would I multiply everything by? 3. So 3y equals 5x minus 7. And then bring your y over. Good times. I like to get rid of my fraction first. You could bring the y over and then times everything by 3. But it's really your call. Yep. In general form, there cannot not be fractions. That's just the rules of general form. You want to be in the general form club, can't have fractions. Okay? All right. Says for the linear function, 32x plus 4y minus 12. If x decreases by 2, how does y change? So what is it really talking about here? What is this referring to? If x decreases by 2, how does y change? Slope. We need to figure out the slope to relate it to this, because this is talking about a rate of change, right? So how do we figure out the slope of this guy? Y equals mx plus b. Yeah, so we want to get y by itself. Easiest thing to do is move who? The y equals negative 4y, and then divide by negative 4. Oh, light show. Okay. Did I hit record again? Yep, I think so. Yeah. We're live. Divide by negative 4. Okay, so what's 32 divided by negative 4? Negative 8x. Who cares what he is? Equals y. So what's my rate of change here? Yep, 2 negatives. Thank you. See? There it is again. Who's tired of fourth block? I am. Okay. Okay, so what's my rate of change here? Negative 8 over 1 is my rate of change. My change of y over change of x. Not 0. Okay, and we want to say if x decreases by 2, how does y change? So it has to be positive or negative 16? Positive 16. So change of y has to be positive 16. Does everyone know how Tyler got that? Or almost got that. Right, so you could cross multiply if you want, even though I really don't like cross multiplication. Right, or we're trying to get delta y by itself, so the more appropriate thing to do would be multiply both sides by -2, which gives you, and then this way the -2 cancel out, and delta y is by itself. So 16. Yeah. So you don't get this part? So this is our rate of change, right? Our rate of change, or a slope. And so they're saying if x decreases by 2, how does y change? So we know that our rate of change is -8/1 for this line. So that's the relation. And there, so we're setting up an equation here. Because the slope equals slope. Really, right? They're talking, it's the same line. So if this is my rate of change, I made it into a fraction. And that's equivalent to what we want to figure out. Okay, if that's our rate of change, what would y have to be if x is decreasing by 2 to give that same slope? Okay. All right, so now that's the easy stuff. Now we get to go into some, I don't know. Okay, anyone want to define what a tangent line is for me? Okay, somebody give me a definition. Don't look at your page. What's a tangent line? Okay, so a line that touches the circle only at one point. Very good. Any other definitions? Does a tangent line have to be on a circle? No, it doesn't have to be circle. No, so with the definition, a straight line that touches a curve or a line only once work all the time. So we're gonna. Well, let's talk about that. Okay, so yes, for a circle, that would be appropriate definition for a tangent line. It only touches the circle once. Okay. You guys are so mean. Is that better? Sort of? Okay, so draw the line. Come on. Okay, so for circles, a tangent is a straight line that touches the circle only once. Okay, but unfortunately, we're dealing with things that are more than just circles. We have curves. So if we kept the same definition, I'm going to call this one T. I'm going to delete this link. We will. I want to move them down. Get out of the way. There you go. Okay, and I'm going to draw another line, L. I don't know why I made it vertical. I don't want to make it really vertical. What is L doing there? Well, here's the problem. Would you agree that L also only touches the curve once? Would you agree that L only touches the curve once? I'm not asking is L a tangent. I'm saying.
Keep going or not? No, there are no arrows.
Yeah, it keeps going, but it's going to go outwards. It's no. Okay, so right here's our curve. It's going to keep going. Here's our line. It's only going to ever touch it once. Right? Yes? Okay, so both L, write this down, both L and T listen up. Okay, both L and T touch the curve only once. The curve only once. However, Greg, are you getting this down? But only T is a tangent. Okay, so here, L and T both touch the curve only once, but only T is tangent. And here, how many times is it across the graph? This is supposed to be just touching here. Twice. So here, the line T is still a tangent. Tangent line, even though it crosses twice. So we are running into some problems here, defining it for things other than circles, right? So if we want to define a tangent and not talking just about a circle, we've got some problems. Okay, so I don't know if I want to look at these ones. I have other ones. I just want to see what these were. Okay, so to illustrate how we come to a definition for tangents, we're going to consider the next example. Where do I move these? Up here. We'll get to those in a second. So here's our equation, y equals x squared. And it says find the equation of the tangent line to the parabola y equals x squared at point 2 and 4. So let's approximate 2 and 4 right here. I'm going to do some drawing. If you have different colored pens, it might be helpful for this lesson. If you don't, that's okay. Just saying, if you do, you might appreciate it. Just because there's going to be a lot of lines, and I know. Sorry. So down below, it says problem. We need 2 points to calculate slope of a line. Right? So we're going to draw this tangent line T here. I'm going to grab my handy dandy line drawer. They're really helpful. Okay, so if you can draw a line T for me, I'm going to make it green. Okay, so here's my tangent T. Fortunately, green is purple. So draw a tangent line T. So we need 2 points to calculate slope of the line. Right now, how many points do we know on this line? 1. Uh-oh. And we don't know the equation of the line because that's what we're trying to find. Yeah, we know a bunch of points that aren't on the line, okay? This is a problem. Right now, do you have enough information to find it? Okay, go ahead. Okay, I'm going to, okay. You guys are smart. Okay, so we introduced another point. We're going to introduce another point on the curve, and we're going to call it Q. And that's x comma x squared. Why is it x comma x squared? Yeah, that's what y is, right? So y is equal to x squared. Okay, so we're going to call this point Q on the line. So we're going to draw it anywhere on the line. Yes. No, we don't. Not this line. Well, we want the equation of this line. Okay, so we're going to draw a point Q. So I'm going to draw Q. I think I drew it over here. Okay, so I'm going to use red. Here's Q, x comma x squared. I should have made P a little higher, but that's okay. And what we're going to do is we're going to introduce a secant line that goes through, oh, this is P. We have to label this guy as P. P, right? That's P2 for our point. And so we're going to draw a line going through P and Q. So get your handy dandy line makers. I think yours are called rulers. Calculator lids also work handy dandy. I don't know, sorry. Don't ask. Okay. All right. So there's my, oh no! Lock. That's why you gotta lock the page. Control Z, Control Z. I don't know if there's Control Z in this notebook. No!
Control Y.
Okay, that's okay. This is what we're gonna do, guys. There you go. And you know what? Control K is gonna lock this baby. It's not moving now. Okay. We're good. Okay, so what are we gonna call this guy? This guy's gonna call this, we're gonna call him a secant line. Yep. Secant. I was going to try, so a secant line. Okay, so I'm going to write some notes for a second here, okay? Okay, so some notes to write on the sign here. How can we use the secant slope to find the tangent slope? No. How can we use the secant slope and the secant line? Did we label it L yet? Let's label it L. Line L. Shh. Doesn't really matter. Oh, I've already used L in my notes later on, so we got to stick with L. For line. Okay, how can we use the secant slope to find the tangent slope? Okay, that's our first question. All right, I'm going to do some labeling here before we do anything else. Okay, so we're just going to take Q, and what's the y value for Q over here? X squared, and the x value is x. And then here, what's the x value for P? 2, y value is 4, 2 squared. Yeah. Okay. Huh? Okay. So here's the thing. We have this. I'm going to show you a little animation because I think it'll make for better learning. So what we got to do is we have this secant line, and what we want to do is we want to bring Q closer and closer to P. Why do we want to bring Q closer and closer to P? Right, so as it gets closer and closer, it's going to basically be the tangent line. I have a few different ones. So here we go. Here's our point that we want to make tangent. Here's my Q, okay? So we want to bring this closer and closer and closer and closer, because what happens with our slopes? Do they become really close to each other really as it gets closer? Yeah. In fact, and if we can get so close, it's basically the same point, our secant line and our tangent line are going to have the same slope. Okay, so we want to bring this, because that's how we're going to find the slope. Because otherwise, I don't know else how you're going to do it with just one point. Okay, so here we go. Here's some other stuff. We'll get to this formula later today. But we want to bring that point closer and closer so it becomes our tangent line. And that's our goal in calculus. So we're going to write that down. Oh, we can. You'll see. Well, in the beginning with limits, we're going to approximate it basically. You'll see. Okay, so the main idea is to start moving Q closer to P. I feel like Q got moved. Oh well. The main idea, well, this should be a little lower, right? Getting this down, Greg? The main idea is to start moving Q closer to P. So in calculus, I have another big paragraph, but I don't know if we want to write it. In calculus, we attempt to bring Q right to P, so that L, so we want to bring, I'll try and shorten this, Q to P, so L becomes who? T. So M becomes T. In this way, the slope is exactly the same. Why? So the slopes are the same. How do we do this? Limits. No. Well, it's because there's two lines. So we're working with the secant. You said it way better than I did. Okay, so the secant line has 2 points, so can you find the slope of that line? Because we know the point Q, so that it actually, at this point, is at the same slope. No, but as we move it closer, will it be the same slope? Okay, let's keep going. Okay, so we introduced Q. That's what we did. Line PQ is called secant. It's approximation of the tangent. Let's move on. Okay, so unfortunately, you're gonna have to kind of flip back and forth because we're still in the same part. Okay, so with the secant, what are my 2 points? P was 2, 4, and what was Q? Instead of xy, we're gonna use x squared. This way it's all in terms of x. Okay, so we want to use the slope formula. What is the slope formula? y2 minus y1 over x2 minus x1. Okay, so let's make our slope. So y2, x squared minus 4 over x minus 2. Okay, can we do anything with this guy? Difference of squares, factor. What does x squared minus 4 become? X minus 2, x plus 2. That's a 2. Over x minus 2, what happens? Just becomes the slope of our secant line going through 2 and 4 is x plus 2. Oh, this? y2 minus y1. Sorry, guys. It's the slope formula. So this is PQ, slope of PQ, our secant line. y2 minus y. Is that better? Sorry. It's easy to get sloppy up here. Slope of the secant line. Have I been gone this whole time? Is x plus 2. Okay? And so we want to approach 2. X equals 2. Why do we want to approach x equals 2? That's where point P is. That's our tangent line. So we want to take our secant and we want x to approach 2 there. So we're going to approach 2 from both sides, the left side and the right side. It's best if we do 4 or 5. So we'll start at, say, 1 on this side from the left. So the left of 2, if this is 2, right, we're going to approach it from the left. We want to get really, really, really close to 2 without actually getting to 2. So here, we'll start at 1, then we'll do like 1.5, 1.9, really doesn't matter, 1.99, and then 1.999. So we're getting really close to 2. Okay, and as we get close to 2, this is the slope of my secant. What is it going to become the same as? Approximate the slope of my tangent. Okay, and we're also going to approach it from the right. So the right of 2, so like 3, sure, and then 2.5, and then 2.1, and then 2.01, 2.001. Sure. So 4 or 5, at least, when we do a numerical approximation. So this is numerically. Okay, so let's plug it in. So our equation of the secant line is x plus 2. So 1 plus 2 gives you 3. 1.5 plus 2, 3.5, 3.9, 3.99, 3.99999. So as x is approaching 2, what is our slope approaching? 4. And it needs to approach the same thing from both sides. It doesn't always happen that way. Okay, so let's do from both sides. 3 plus 2, 5, 2.5 plus 2, 4.5, then 4.1, 4.01, 4.001. Oops, too many zeros. So what is it approaching on this side as x approaches 2 from the left, right? Also 4. So because it approaches it 4 from both sides, we can say the slope at that point, our tangent line is 4. Okay, let's move on. So we say the slope of the tangent line is the limit of the secant slopes. So we could say, I don't know if I have all this stuff. Because it represents the limit of slopes as x gets infinitely closer to 2. So we call that the limit as q gets closer to p. For our slope of PQ, it's going to become our tangent line. Okay? So, or the limit as x approaches 2. And then what's this? What did they replace here? The slope of PQ. Right? So this is the same thing. Just rewritten. And then what did it equal? 4. Okay, so wants the equation. So we know the point was 2, 4. What's our slope of the tangent? 4. So can you find the equation now? In, yes, general form. It's proper. Can we find it now? Yeah? Which formula? Y minus y1 equals m times x minus x1. Now what? Plug it in. Y minus 4 equals 4 times x minus 2. So y minus 4 equals 4x minus 8. Bring everything to one side. Minus 4. Okay. I don't know if that made sense. We're going to do another example. It's very theory-based. Well, it's getting closer and closer and closer. So another way to think of it is once I read this thing about duct tape, right? And if we were supposed to take someone in this classroom and we want to duct tape them to a wall so that they're like not on the ground, like hanging with duct tape. Okay? There's a limit about how much duct tape you actually need, right? There gets to a point where too little, is that going to work to hold them? No. And then we also get to a point where there's too much. And if we want to limit the amount of duct tape so that we can exactly get that person with the least amount of duct tape needed to hang that person, there's going to be a limit on that. It's, well, in that case, there's like a minimum. Yeah. So I thought it would be a fun thing to actually try, except for I don't know if I'd get in trouble if we actually did that. So I was like, nah. You guys actually did that? So I won't lose my job? Huh. That's cool. But there a minimum, like, did they limit your amount of duct tape or did you have unlimited? Oh, yeah, so they limited your. Okay. That might not have been the best explanation. I can't speak today. Okay, so let's move on. Let's do another example, okay? So for the function y equals x squared minus 5x, determine the equation of the tangent line at point 2 and negative 6. Include a sketch. Find the formula for the secant slope. See what the slope approaches as x approaches. This should be a positive 2. Because here it's positive 2. Okay? From both sides to get the tangent slope. So let's start by sketching this. Zeros. What would be the zeros of this function? Let's factor it. 0 and 5. 0 and 5. Okay. Okay, so we have our point P. Where's point P going to be? 2 and negative 6. So there's my point P, 2 and negative 6. And we want to find the equation of the tangent line. Oops, that is... No, it's not even close. That's a little better. There you go. Sort of. There's our tangent line. Okay, so what point do we have to introduce? Q, and what's Q going to be? I'll put it on this side. So if instead of xy, we'd say x, comma, what's our y equal to? X squared minus 5x. Okay? I can probably do dotted lines. I don't either. It's really thick, eh? Okay, I'm sorry. It's gone. You're gonna... It is an ugly line. I hear ya. Okay, so we want to bring... Oh, that's not even like close. We'll get it. We want to bring our new line. He laugh at you. Okay. So we want to bring this PQ, this line QP, right? We want to bring Q closer to P, closer and closer. So what's it going to happen? It's going to turn into, as it moves down, this line is going to become almost P, if not T. Okay, so what's the slope? Our slope of PQ, let's find it. So what are our 2 points? X squared minus 5x and x. That's one of them. What's the other one? 2 and negative 6. Let's go the other way around though, right? Like this. Oh, I should lock it. Minus 5x. Unless you still have it in factored form. Stop it. I need to lock it. Okay. I don't know. I should do this ahead of time. Okay, so maybe it'll make, yeah. So our equation, y2 minus y1, what is it going to become? X. You kind of want to have this guy first, right? So it factors nicely. So x squared minus 5x minus a negative 6 becomes plus 6 over x minus 2. So we factor this guy. Probably two numbers that multiply to positive 6 add to negative 5. Oh, you guys, factor. You're fast. Okay. Woohoo! Oh, look, we can cancel. Now, why is this a good thing? Let's talk about something. Why is it really good that it cancels? We actually needed it to cancel. Why would we be SOL? Is that what it says? That's a bad thing to say. But why would we be in trouble? I don't know. I don't know what it means. Okay, so why is it really important that something canceled here? Think. What are we approaching?
One thing.
What number? What do we want our line to approach? X is 2. We want it to approach 2. X cannot equal 2 if it, right? It's a non-permissible value. So that's why it's really important that this canceled here. Also, would we have been able to find our non-permissible value? Or sorry, would we be able to find our slope? No. So, right. So now, could you plug 2 into that equation? Now we can. So we're not, it's a little bit different than solving a rational equation. Yeah. Okay. Okay, so we're not solving, be careful. It's, in this case, it had to cancel because it's, what we're approaching is always going to be our non-permissible value. So it always has to cancel. The reason why is because this is our point, at, right? It's always going to be x and then x minus 2.
So if we end up
And so that's always what we're approaching. So it has to cancel, else we couldn't find our slope.
If we end up with not canceling like a test, we should know we're wrong.
Well, we're going to have a special name for that, and then you're going to have to somehow rearrange the equation. And so, because limits, here's the thing about limits. A limit, and we're going to get into this in more detail, just because it's a non-permissible value, or like a hole in the graph, doesn't mean the limit exists. Because the limit is basically what is the number approaching from both sides. So even if it's a hole in the graph, a non-permissible value, the limit is different than the actual point. The limit is saying, what is it approaching from both sides? Is it approaching a number from both sides?
So it's not the actual answer, it's just what it's approaching.
What's it approaching? Yes. The limit is what is approaching from both sides. That's what the limit is. Okay? So, I don't know if I just made things, I don't know. Okay, so x minus 3. That's our, so we want to approach it from both sides. We're approaching x. As x approaches 2, we want to see what our secant slope approaches, which is x minus 3. And we need to do it from the left and from the right. So left-hand side limit and a right-hand side limit. Okay, x approach 2, slope of the secant is x minus 3. We'll do 4 instead of 5. Do 4 or 5. So instead of starting at, let's start pretty close. I don't know. So left-hand side of 2. 1.5, sure? Ben? Let's go a little closer. 1.9. This is usually what we do in limits. And then 1.99, and then 1.999. It's often how it looks. Well, why wouldn't you not use another 9 instead of a 7? It's even closer. Okay, right-hand side of 2. So right-hand side of 2 now. Sure, 2.5, 2.1, 2.01, 2.001. Okay, so you're going to come up with these numbers. That's your job. Okay, so what is our slope approaching? Let's figure out. 1.5 minus 3. Negative 1.5. 1.9 minus 3. Negative 1.1. 1.99 minus 3. And then, okay, let's try the other side. 2.5 minus 3. Negative a half. 2.1 minus 3. 2.01 minus 3. Okay, so you can use your calculator for this. Let's plug them in. So, as x approaches 2 on our secant line, what is the slope approaching? Negative 1. Has to be the same from both sides. So, on both sides, the slope is approaching negative 1. Yeah, it is going down. Okay, so go away. Go away. Just won't leave me. There you go. Okay, so now can we find the equation? Okay, so by the way, how we'd write this is we could say the limit as x approaches 2 for what was the equation for our secant line? Over x minus 2, the original, equals negative 1. That's how we'd write that. And that's equivalent to the slope of my tangent. We'd say, or approximates the slope of our tangent. So here we go. You won't always. There's graphical methods, there's numerical methods, there's a formula. So that's one method you need to learn about. Yay. So that's today's lesson. No. In the future, yes. In the future, yes. For today's lesson, no. Because technically, if you'll notice, if you just plugged in 2, 2 plus 2 minus 3 is negative 1.
So that represents the x squared minus 5x plus 6 over x plus 2. That represents the slope.
Of the secant line.
Right.
Because rise over run. Because it's asking, so the question's asking us, and so what's really important about this concept is for the first time ever, we can find slope at any point now. Right? Before, like, you need 2 points. Okay? So what this is going to mean for us is a lot of things. In applications, we're going to relate it to velocity. Shut up. It's really ugly. Okay, so now that's what limits does. We can now find the slope of a tangent line with only 1 point. Why? Because we introduced a new point. We make 2 points. But before, you could never find the slope of a tangent unless you knew 2 points on that line. It also is really cool, is because now we can find the slope at any point on a curve. That's crazy. That's so cool. It has so many applications, it's not even funny. Hey. Well, if you knew that point, if you knew 2 points, then why wouldn't you just use that? Yeah, absolutely. But in all of these, we're always going to be just given 1 point. Yeah. So, so like if we have a distance time graph, what's the slope going to give you? Velocity. And so we can get the velocity at any particular point even if it's changing, which is where a lot of the physics formulas are derived from. Derived. Oh, derivatives. That's what they're used. Yeah. Okay. All right. Oh, we're not done, guys. We still need to find the equation of the line. What? Right? Went through 2 and -6. Slope equals -1. Oh, we have to go sign out our textbooks. Hooray. Okay. Let's do this really quickly. Y plus 6 equals our slope times x -2. So -x plus 2. I'm going to bring the x to this side so that I don't have to flip the signs. So x plus y subtract 2 would be 4 equals 0. Hooray! Yeah. Okay, so that's 1.1. That's the end of this part of the lesson. We're going to do half of 1.2, but first we're going to take a break by getting your textbooks. So go to the library and go get your textbook.